I'm one of your professors in biomedical engineering. I'm going to be discussing with you the motor system, which is the system that allows you to obviously come, walk, and express everything that's central to our ability to move. So the motor system is a reflection of the way you make decisions. So I want to start with a very simple idea for you. So we put value on any action that we perform. So for example, you decided to come to class today because there was a value associated with coming and sitting down and listening to me. And that value was higher than staying in your room or throwing the frisbee. That value decision reflected in what you did. But that value decision also affects how you move. The basic idea is that you will move more vigorously toward things that you like as compared to things that you don't like. The basic idea is, if you want to know how much somebody cares about you, just pay attention to how they move towards you. They're going to move more vigorously towards you if they value you. You can see it at the airport. When you see people come out of the security area, it's not hard to tell who knows each other and who doesn't, right? People who know each other run toward each other. They hug each other. And people who are just waiting for somebody to have a sign up or something, well, they don't move very much toward each other. So the value that your brain assigns to stimuli around you dictates the action that you're going to perform. But that also affects how you move toward that stimulus. So things that affect the value system, like Parkinson's disease, it affects not just the choices that the patients make. What do they want? What do they not want? But also how they move. And so many of the disorders that affect the brain affect not just the psychiatric aspect of the action selection and what is it that they would like to do, but also how they move. An obvious example of it. When you're depressed, do you move the same way as when you're not depressed? Some people, when they're depressed, they can hardly get out of bed, let alone walk. So some of these influences on our brain affect the choices that we make as well as the way we move. And so the series of lectures that I want to give to you describes the relationship between this value function and the way you move. And that these are overlapping things. The way you make choices, the way you describe effort, the way you imagine reward, not only affects what you choose to do, come to class today, but how you perform that action, the vigor by which you express what is it that you've chosen. This influences many regions of our brain. We're going to talk about these various regions, what dictates the final output, which is the movement. So I'm glad that you're here, and I'm going to be talking about this problem of how to move, and I'm going to tell you that basically the way you move is a really wonderful way to make sense of how you're thinking and how you're evaluating the stimuli around you. Let's begin with a simple system. This is the sea cucumber. It's a multicellular organism. And the reason why to start with this simple structure is because it has this interesting property that basically it has this very simple spinal cord and a very simple sensory system that detects nutrients in the water, and it uses it to find a place to go place its head, and the head is down here, and plant itself. And then once it finds that place, it basically digests its own nervous system. So it has a nervous system for the purpose of finding a home. Once it finds the home, it doesn't need to move anymore, and therefore it gets rid of its nervous system. So upon finding a suitable substrate, it buries its head and starts absorbing most of its own brain. So what separates us from plants is that we can move. And to control our movement, we've developed a nervous system. If you don't need to move voluntarily, you don't need a nervous system. So obviously plants, they don't move voluntarily, and they don't have a nervous system. Every animal that moves voluntarily has a nervous system. So one idea is that the reason why you have a nervous system is because it allows you to control your movement. Sensing things is nice, but it's worthless unless you can do something about it, which is controlling your movement. All right. What are you looking at when you look at this painting? So in the 1950s, there was a graduate student in Russia who wanted to know, do we direct our eyes to locations on a painting based on things like your favorite color or based on some pattern of scanning, or how is it that we direct our actions toward things? And his name was Yarbus, and he came up with a way to measure your eyes, the position of your eyes. And what he noticed is that it didn't really matter what was your favorite color. It didn't matter whether, I had told you to look for foliage. What happens is that when people looked at this image, they tend to concentrate on these bears, animate objects. And when he looked at that data, so here's the data where people were looking, what he thought about is that, well, it seems like people are directing their eyes toward things that they value. And so animate objects are valued more than inanimate objects. Which is why, if you pay attention to when you open a website, pay attention to what is it that you look at first. Where do you direct your eyes? Because that tells you something about how you value images. And most of us direct our eyes toward faces, particularly female faces. So humans like faces. Faces are an important value quantity. And we direct our actions, we direct our eyes, our gaze, toward things that we value more. So the first idea is that basically by looking at where people direct their eyes, you get a sense of a value function. What is it that they value more? Does that make sense? Because that's where the reward is located, right? When an image is shown to you, it's just a bunch of pixels. Your brain analyzes that image, assigns value to different parts of it, directs your gaze toward the part that to you is most valuable. And so what you're seeing when you're paying attention to where you're looking is what is it that your brain values more? Because that's where it says, that's where reward is. That's where I'm going to direct my eyes so I can harvest that reward. I can consume the reward that's there. All right. So we can look at this also for other kinds of movements, not just eyes. In this case, this is a pointing movement. So there's a screen, there's a circle there on the screen, and you ask a person to make a rapid movement there. And if they hit that green screen, you're going to give them 100 points. So what they're going to do is to direct their hand to be at the center of this thing. And you see that every trial that they make, there's some noise. And on average, the center of this noise pattern is around the center of this circle, because that's where the reward is. Now, if you put a distractor there, say, if you hit the green, I'm going to give you 100, but if you hit the red, I'm going to take away 200, and if you hit someplace in between, I'm not going to give you anything. So now give them a penalty, a cost. What do you think is going to happen? Where are they going to aim? Yeah, more to the right. So if you look at the distribution of their behavior, they're going to aim more to the right. So they're going to miss a number of times, they're going to hit a number of times, but on average, they're going to try to maximize their reward by aiming a little bit away from the penalty. And if you increase the penalty, they're going to go even farther away. Does that make sense? So through their actions, they are maximizing their intake, their reward. So in this case, you're going to have some cost, and so you're going to veer away from the place that's going to cost you. So if you increase the noise, so suppose here's a patient that's reaching, they have a greater noise in their movements, what they're going to do is that they're going to aim even farther away. And in this case, you see they're aiming almost outside of the reward zone, so based on the noise that they have, they will sometimes hit the green reward. So the behavior is such that it tries to maximize the sum of reward minus the loss. And in this case, it would require you to go even farther away from the center. Do you have any questions about this? Yeah.
What exactly is the noise here?
I'm sorry?
What's the noise here?
Well, every time that you perform the action, you're going to have some stochasticity in your behavior. And that comes about because the neurons are noisy, the forces that you produce in your arm is noisy, and when you hit it, sometimes it's to the left, sometimes to the right. Does that make sense? And so, given the noise that you have, you're going to try to optimize your behavior so that you get as much reward as possible. If your noise is great, like this, you're going to have to aim even farther away. Okay. All right. So, the idea is that the decisions you make about how to move, where to move, depends on the reward structure. That reward structure identifies the action. This course, this part of your course is about how do you actually perform that action. What parts of your brain are involved in it. So from the onset, I want to dissociate between two kinds of stimuli. One kind of stimulus is a place, is a location where you're going to find reward. Maybe your parents' home is such a location. You feel comfortable there. It's a nice place to go. It shelters you. It provides you with food. That's a nice place. So that's a location where reward is found. That's different than a stimulus that represents a symbol, like a face, that would give you pleasure. Maybe the picture of someone you love. These two different kinds of stimuli, location and object, are going to be engaging different parts of your brain and are going to cause movements that are originating from different regions. And so I want to briefly describe to you behaviors that are goal-oriented toward reward, one toward a place, one toward an object, and show you that if it's toward a place, then what matters is the hippocampus. If it's toward an object, then what matters is the basal ganglia. All right, so this is a mouse. The mouse is thrown in a pool of water. And the pool of water is milky, so it can't see that there's a platform out here. And of course, it would like to go find that platform. And this platform is in a room where there are markers on the wall. So if the mouse understands that this platform is close to this triangle, then next time that it's thrown into the water, it will find that place quickly. So it needs to learn a map that says there's something good next to this triangle here, that location. Wherever this triangle is, that next to it, there's a place in space where I'm going to be able to find my rewarding region. And what you see here is that after training, a healthy animal finds this region very quickly. Now what's happened here is that in this experiment, after the animal has been trained, the platform has been removed. So what you see is that the animal is constantly swimming in this quadrant because that's where it expects to find that stimulus, that platform. But in an animal that has had a mutation that's affecting learning in the hippocampus, the animal doesn't know where that stimulus is, despite the fact that he's observed that location many times. And so a location that's associated with the reward, in this case getting out of water, is associated with the hippocampus. Associating reward to a location on a spatial map depends on the hippocampus. So the famous patient in neuroscience, Henry, HM as he's called, had damage to his hippocampus. And he had a number of issues. He had lost immediate memory, short-term memory, and so forth. And he couldn't form long-term memories. And one of the problems was that he, like what you see here, had a deficit in understanding these spatial maps. In contrast, let's look at another version of this experiment where the stimulus here now is not going to be what's on the wall and the location of this platform with respect to the wall, because every day the location is going to change. But what's always going to tell the animal the location is this green flag on top of it. So there's another flag, this gray flag, that also identifies another platform. In this case, the platform is small, so the animal cannot stand on this. Whereas here, the animal can stand on it. All it has to learn is that this green flag tells me where the platform is. Not its location with respect to the surrounding, but the fact that there's a green flag on it. And the objective is to show you that when there is damage to the basal ganglia, in this case the caudate nucleus, which is a part of the basal ganglia, the animal doesn't learn. It doesn't learn that what determines this rewarding location, this stimulus, is this green flag. Whereas damage to the hippocampus, part of it called the fornix, has no effect. The animal learns it anyway. So, reward associated with location seems to depend on the hippocampus. Reward associated with a stimulus, like an object, seems to be associated with the basal ganglia. All right. Do you have any questions about this so far? Yeah.
So certainly, like there's correlation between those two events, but how do you actually know one is causing the other?
Right. So you can think of these systems as parallel learning systems, where you have things that are competing with each other. Of course, the animal doesn't know from the beginning whether it's going to be the location that's important or the flag, right? And so the typical experiments is to show that both of these systems are learning, and if you damage one, the animal relies on the other. All right. So we've been talking about reward, and I just want to briefly describe a little bit about the reward system in the brain, and that's what we know most about is the neurotransmitter dopamine. So dopamine is released from neurons in the brainstem. They project to three main areas: the basal ganglia, the hippocampus, and the prefrontal cortex. And basically, dopamine seems to have a lot to do with this learning to associate stimuli to reward. And forms of learning called reinforcement learning, which is the basis of so much of artificial intelligence today, teaching machines to play games, teaching machines to drive cars and so forth, all have arisen from mathematical models of learning that have to do with things like dopamine, called reinforcement learning. And so it's really an interesting example of how algorithms that were first designed to try to understand how the brain learns are now becoming some of the most powerful ways for machines to beat us in games that we used to play well, like Go and other games like checkers. So dopamine is what's released from these brainstem structures. And let me show you what dopamine does. What does it look like? Basically, what dopamine appears to do is to tell the brain that there is a value associated with a stimulus. And if that value is higher than what I expected, I'm going to get a burst of dopamine. If it's lower than what I expected, I'm going to see a little bit less than normal amounts of dopamine. So it tells the brain, first there's something rewarding, and then when the reward comes, it tells you whether you got what you wanted. Was it as big as you expected? Was it better than what you expected? Or was it worse? So let me show you the experiment. So the animal is looking at a screen and there's a visual stimulus that appears. Now normally this visual stimulus doesn't give the animal any water or juice. So in this case it's a monkey. Monkey's looking at a screen. There's a stimulus that appears. Sometime later, all of a sudden the monkey gets juice and the monkey's thirsty. When the monkey gets the juice, which is at this time, there's a burst of activity in the dopaminergic cells. Now P here tells you the probability. So it's almost zero. So almost never the animal, when it sees this stimulus, is going to get this juice. But in these trials, there was those rare trials when the animal did. So it got surprised that it got juice here, got the reward at this time, and there's a burst of dopamine. So it wasn't expecting juice, but it gets it, and it really likes it. Dopamine is released. On the other hand, at the bottom case, the probability is almost 1 that they're going to get juice, which means that when the stimulus appears, the animal knows that it's going to get juice here. What's interesting is to notice that the occurrence of the stimulus itself causes release of the dopamine. The animal doesn't have to actually get the juice for the dopamine to be released. Of course, it predicts that I'm going to get juice, and indeed it gets juice, and you notice that the stimulus itself is sufficient to predict the reward. So what's happening is that dopamine is released if you expect the stimulus to give you reward, which tells us, it's telling us something about the value of this stimulus, and it's a valuable stimulus for me. And that if, on the other hand, I didn't predict that it's going to give me a reward, and it does give me a reward, then what's going to happen is that that stimulus, the occurrence of the reward, is going to result in dopamine because it's better than I expected. On the other hand, if I predict reward and I get reward, that's no difference there. So it's predicting I should not get reward, but I did get reward, so I'm really happy. It's predicting that I will get reward, and I indeed did get reward, so there's no effect of reward itself. The stimulus itself is rewarding. I don't actually have to get the water to get it. So this is a reward prediction error, right? So here, I predicted it and I got it. There's no difference. I didn't predict it and I did get it. So it's much better than I expected. In between, it's half and half. So if half the time I'm going to get reward, then when the stimulus appears, I have some expectation of reward, and when I get the reward, I'm occasionally surprised. So this model of learning says that dopamine is telling the animal whether the stimulus has value, and when the reward arrives, whether that reward was better, equal, or worse than what the animal was expected. And this dopamine is the neurotransmitter that is lost in Parkinson's disease. This is what's affected when individuals suffer from this neurodegenerative disorder that kills the dopaminergic cells in their brainstem, the basal ganglia. Okay, let me see if you have any questions about this. So we think reward is encoded through dopamine. Effort is probably also recorded through dopamine. We have less evidence for that, meaning that if the animal has to work to get the reward, the amount of work that the animal has to do to get that reward is also influencing the release of dopamine. Maybe different dopaminergic cells signal goodness, reward, effort, the work that you have to do to get it. That's less understood at this stage. All right. Now, at the beginning of the lecture, I mentioned to you that reward not only affects the choices that we make, but also how fast we move. Meaning that the stimulus that tells you there's going to be something good here not only says you should choose that over the other stimulus, but that you should move more vigorously, more strongly, with a shorter reaction time, with a greater velocity toward the stimulus that promises you greater reward. So let me show you an example of that here. So in this experiment, the animal is moving its eyes to stimuli on the screen. One of the stimuli is associated with reward, the other one is not. So when the animal makes a saccade, moves its eyes to the stimulus that's associated with the reward, it's going to get some juice. That's a valuable stimulus. At some point in the experiment, that stimulus that was associated with reward goes away and is no longer associated with reward. Now a new stimulus is associated with reward. And what we want to see is what happens in behavior of the animal. So on the left side here, what you see is the saccade latency. That means when the stimulus is presented, how long did the animal need to make a saccade to that stimulus? Here in the red is no reward trials. which means is that the stimulus is presented, the animal moves its eyes to it, it won't get any juice for that. At some point, all of a sudden, this trial here, the first trial in the blue, the animal makes a saccade, but whoa, he's going to get juice for that. So the next time that that same stimulus is presented, what you notice is that the reaction time falls. So it used to take it 300 milliseconds to move its eyes. Now it takes only 200 milliseconds to start that eye movement. Reaction time becomes shorter because all of a sudden that stimulus that was not rewarding becomes rewarding. And the animal now moves with short reaction time. And then here, this stimulus, the first red one, is the same stimulus as before, but no longer rewarded. So the animal makes a saccade to it, expecting to get juice, does not get juice. Next time he sees it, he moves a little bit later, is not as interested in it anymore. So the reaction time that it takes for the animal to move toward the stimulus depends on whether it expects reward. You will move more quickly and earlier toward things that you value more. This has to do with your basal ganglia and how it is evaluating that stimulus. So here's the basal ganglia. This is the caudate nucleus of this animal. And what's happening? Well, when the animal is requiring a long time before it makes the movement, the activity is low. When all of a sudden it's moving sooner, the activity goes high. So there's a correlate of this reward in the way the animal moves, and in the basal ganglia there's activity that's associated with that movement. So you can begin to see that when you have a disease that affects the basal ganglia, like Parkinson's disease, it would change the way you will move because that value function has been affected. It will no longer be invigorating the movement because the value is high. Any questions about this? Yeah.
I have one that's kind of it's a little unrelated. Like you said, like rewards. What about something that's like scary?
Yeah.
It's not like reward,
Right.
but it's still something that we value.
Right, right. Excellent question. So, number of ways to think about that. You can think about risk. You can think about loss. So these are terms from economics, right? So you can begin to see that economics, the terms that are used to describe how you make your decisions, losses that you might incur, probability of loss, which would be the risk that would be involved, these things all go into that value function. It's not just reward and effort. It's also things like losses. And there's this term called loss averse, which means that you would rather not do this because the small probability of loss makes it unworthy of your choosing of that action. And these terms all go into this function, this mathematical function that describes value. And that value will affect how you choose. That's the field of economics. What did the person choose to do? Did they pick object 1 or 2? Did they pick a jam that had this color versus that color? How should we advertise to the people so they can move their eyes toward it? How should we make a website so they could pay attention to it? These are the things that determine how the value function in your brain works. And that same value function probably affects how you move. Now, the components of this are just beginning to be understood. So far, we know something about reward and the function of dopamine. Effort, much less so. Risk, much less so. And losses, much less so. Then there's this concept of attention, right? Because attention is also associated with this. A bright light will get your attention more than a dim light. So that's the neural correlate associated with it. And is that a value associated with it? That's even a more complicated scenario. So down the road, 15, 20 years, you might see this convergence of fields of economics and neuroscience into some coherent form that begins to understand decisions and actions together. For now, just going to stay with the basics. Okay, so far what I've been talking about is the concept of reward, an expectation of what is it, the purpose of this movement. That's really just the beginning of the story, because the goal is to improve your state, right? So you come to class today because it was better than staying home. You hope that at the end of this class you get something that you would not have gotten if you stayed home. That was an expectation that you had. Every movement you make is based on this expectation, that at the end of this movement, I will have a better state than if I had not moved. But how do you actually make the movement? Well, what you have to do is to take this value function that says, at the end of this movement, there's going to be something good for me, reward, and you're going to have to pay some cost to achieve it. But you have to move, right? You're going to have to get out of bed and walk to class. You're going to have to do A, B, and C before you get reward. You're going to have to expend effort to get it. And the question is, how best can I do this? How best can I get the most amount of reward by spending the least amount of effort? That's the translation of this value to the motor commands. And that's called a control policy. A control policy tells you how best to translate this objective function, a mathematical representation of costs and rewards, into an actual action. How should I move my eyes? How should I walk? How should I reach in order for me to maximize this value function? Once you have the motor command, you've generated it, you then change the state of your body. You begin to reach. You move your eyes. Now, as you do that, sensory feedback comes back. Says, you're moving your legs, you're moving your arm. After a time delay, I'm going to tell you what happened. So you generated these motor commands, and these were the sensory consequences of it. But because of the delay in the sensory feedback, the control of movement is not nearly as good as it could be, because movements are noisy, as we saw when you were trying to hit that target. You have variability in your behavior. So what the brain takes advantage of are models that say, if these are the motor commands you generated, I'm going to predict for you what's going to happen. And so you can rely on models to control your movement, in addition to that delayed sensory feedback. I'm going to give you examples of this. And to give you a simple example of it, let me ask you to volunteer. Come on up. Bring your computer as well. Okay, great. Thank you so much. You'll stand here. Stand here, face me, and you're right-handed or left-handed?
Right-handed.
Right-handed. Give me your left hand. Okay. Good. Okay. Just keep it steady. Okay. Now you pick it up. Keep your hand steady.
Okay.
You pick it up. Okay, great. Thank you so much. Go ahead, sit down. So did you see what happened? So when she picks it up, her hand stays pretty still. But when I pick it up, what happens to her hand? It goes up like this, right? Why? What's the difference between me picking it up and she picking it up? Say again? In a way, it's anticipation. She can anticipate her own actions, right? Because it's her brain telling her right arm to pick up the object, which means she knows precisely when to turn off the biceps in her left arm so their hand stays steady. So she's holding this computer by activating her biceps so the hand doesn't fall down, right? So she's activating her biceps, holding this up. When I pick it up, she can see me do it, but she can't react fast enough. And so her arm goes like this. But when she picks it up, she is sending the control to her own arm. She can predict the consequences of that, and therefore she compensates for it. Do you see that idea? Okay, so the lesson for today: when you go to a fancy party and the waiter comes with a tray full of drinks, what do? No. You let him pick it up and give it to you. Does that make sense? Right. Okay. So this is this structure here. This structure that is making predictions. And we're going to learn about that. All right. So this is the high jump. And I want to show you something about this policy, this idea that you take a value function and you learn to maximize it in a real world. So the high jump in the Olympics, starting from the early parts of the 20th century to the later part of the 20th century. So what's the value function here? The value function is jump as high as possible. And the higher you jump, the more likely it is you're going to get the gold medal. So at the early part of the 20th century, humans thought the best way to jump is using the scissor action, like this. So Ethel won the gold medal in 1928 by jumping in this way. Then the next innovation was this, which is the rolling that you do as you cross it. And then this is Dick Fosbury. So Dick was an engineering student at Oregon State. And he thought of a better way to jump. And if you notice, his center of mass is down here. Why? Because his legs are below the bar. So that's one change that took place. But another very important change that took place is associated with that question that was asked earlier, was development of padding, so you don't break your neck when you land. So obviously, he couldn't do this here, right? Because he was going to land on his head on this grass. So the idea is there's a value function that says, what is it that you want to optimize? In this case, jump as high as possible. What are the risks and rewards? Well, reward is you want to win a gold medal. The risks is that you might break your neck. What's the best way to jump? And the nervous system develops policies. And this is a rather astonishing policy because nobody had come up with this before. He was the first person to figure out a better way to jump. Which is, when you think about it, rather astonishing, right? That until this time, nobody knew the best way to jump was to jump backwards with your back to the bar. Okay, now we can't really study these complicated things in a lab like jumping, at least not in typical labs where you have animals and you want to record from their brain, and so you can't have them jump over bars. You do much simpler tasks. And one of the simple tasks that people study is reaching. So here's a reaching task where the subject is holding a pen and is going from this location to this location. And what you tell the subject is that I want you to hit the goal region back and forth as frequently as possible, but not the error region, which is this region next to it. And basically, the idea is that if you take this distance between the two goal regions and you increase it here, and you say that the width of the error region, this region next to it, this region here, is large, then what happens is that, the width of the goal region, if this main place that you want to hit is big relative to the error region, then people reach very quickly. On the other hand, if this region here, the goal region, becomes really tiny, then they reach slowly. So basically, they're going to reach slower, more precisely, when the goal region is small. They're going to go faster when the goal region is large. So the reason for that is because when you move fast, you have greater variability in your movement. Speed makes it hard to control the movement that you're performing. And so in order to optimize your movement, you need to figure out how much noise there is in the way I move. If I want to hit the target as often as possible, I need to know the noise that I have in my movements. And if my goal is large, then that noise doesn't really matter. If my goal is small, then the noise is going to play a big role, and so I need to move slower. So the basic idea is that noise in your movements is going to affect the way you move. You're going to move slower if you have greater amount of noise. Why? Because by moving slower, you have more time to control the endpoint of your movement. That will increase the amount of reward that you're going to get. Another kind of movement that people look at is reaching movements. So a reaching movement is typically done like this. You hold some kind of an object, in this case it's called a manipulandum, and you reach from point to point. You give a target to individuals. You say there's some reward there if they reached it, and you look at how they move. You see people generally move in these straight lines, and they have some particular velocity profiles that they do. And you can modify the amount of reward you give them. You can make it more effortful for them to move, and you can look to see what is the action that they choose? What's the reaction time of their movement? How fast do they move? And how does reward and effort modulate the speed by which they move, the reaction time that they choose to move? So what I'm talking about is that value function and how it gets translated into motor commands, right? So the task for them is to get as much reward as possible. If it's pointing like this, where there's a small region of reward, they're going to move slowly because of the noise in their movements. Okay. Another kind of movement that people study are saccades. These are saccades that are made by your eyes. And let me give you a sense of what a saccade looks like. So here's eye movements that are made by humans. This is the velocity of the eye as a function of time. So a 5-degree saccade, when you're reading a book, let's say, you make a 5-degree saccade, boom, 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 as you're reading the words. Here's what the velocity of the eye looks like. It has about a 200 degree per second maximum velocity. It ends at about 40 milliseconds. So a saccadic eye movement is on the order of 40 to 50 milliseconds in duration, has a peak velocity of something between 200 to 500 degrees per second. So that's how you move your eyes. Extremely rapidly over a very short period of time. And one can ask the question, why? Why do we move our eyes like that? Why don't we slowly move our eyes? Why do we have this very rapid motion of the eyes? There's a relationship between duration and amplitude. There's a relationship between peak velocity and amplitude. So some people have very fast eye movements. Some of you will have velocities of your eye that are 700, 800 degrees per second. Some of you will have velocity of your eyes that are 400 degrees per second. And if you have 700 degrees per second velocities, you have that every day of your life. And if you have 400 degrees per second, similarly. And we can ask the question, why? Why do some people have such differences? It's a similar question to asking, why do some people talk so fast? I'm sure you've noticed some of your friends. Do they also walk fast? Do they have fast saccades? Is there something about their brain that's altering that value function that I was telling you about, making them so that every movement that they make has high vigor? These are questions that we don't know the answer to, but studying them. All right. So let's use a little mathematics now to try to put together some of these stories, because we want to take a value function that describes what's the purpose of this movement and translate it into the motor commands. We're interested in using a formal structure that says this is the reason why you're moving, and if you did the movement, at the end of it you're going to get some rewards and so forth. So what's the mathematics that we're going to use? The mathematics looks something like this. It says there's some cost, and this cost tells you how good is the movement that you're making. Well, at the end of your movement, x here is, say, the position of your eyes, should be at the end is some time p, you should be at the target. And you see this is a quadratic structure. It says I'm going to penalize you the farther away you are from your target. So there's a place where there's reward. The farther away I am from reward, the badder it is, the worse it is. And so by this left function, what I'm doing is to penalize you. Say the closer you get to the reward, the better. Then there's a second term here, it's a cost of time. It says, well, how long did it take you to get there? Well, if you're moving your eyes, while you're moving your eyes, you're blind. So you want to get there as soon as possible. So you want to penalize time. And then this last term here is effort, motor commands that you're generating. And this says the more commands you generated, the worse it is. So basically you want to produce the least amount of effort, get there as soon as possible, be as close as possible to reward. It's very similar to the choices you make when you look at flights to Cleveland. You say, how long does it take me to get there? How much does it cost? It's the same kind of principle. You want to get there, you want to as close as you can to the destination because that's where the reward is. How much effort does it take to get there? These are the motor commands. How much time does it take to get there? That's there. So there's something interesting to one side of your fovea. I want to fixate this interesting thing, and I will incur cost by not looking at it. During the movement, I'm effectively blind. The eye movement should complete as soon as possible. A fast movement requires large motor commands. The larger the command, the larger the noise in those commands. Noisy motor commands produce inaccurate movements. So I want to find a way to move the eyes to the target as soon as possible while minimizing these motor commands. Let me stop for a second and see if you have any questions. Yeah?
Can you go back to the slide with the different regions? Yeah, this one. So when you make the gold region wider, does that increase the reward, or is it the same reward for each width?
Same reward, but it increases the probability of reward. If you hit it, you get reward, but because you have variability and it got big, your probability goes higher. So it's the same amount of reward, but the probability is higher because the region is bigger. Okay, great question. Any other questions? All right. So what's bad about generating motor commands that are big? Why is it that we should not generate big motor commands? Because big motor commands, big amount of force, results in greater variability. Let me show you that here. So on the left side, you have force written as a function of maximum voluntary contraction. So somebody's pushing, and they push a lot, like you see here, or a little bit, or very little. At some point, you remove the visual feedback, so they can't see how much they're pushing. And you look at that variability here. And you see that the variability is high when they're pushing a lot. Variability is a little bit lower when they're pushing a little bit, and hardly there at all when they're pushing even a little bit less. So if you generate force on a force transducer, and if you look at that variability there, that variability scales with the magnitude of the force. The greater the force you generate, the greater the variability in your force, which means the more noise you have in your motor commands. What this says is that explosive forces generate, of course, tremendous amount of movement, but they're hard to control because there's huge variability in the magnitude of that force. Which is probably why it's so hard to throw a baseball, not just at very high velocities, but consistently to the strike zone. Because the greater the force you're generating, the greater the variability in that force. Okay, so this results in motion, and then we have this thing that says we're going to use a model to predict the consequences. So let me show you an example of that. So this was our little picking up task where you come and pick up the object and it causes it to move up. I think I have a video here that I can show you this. Let's see if this works. All right. Okay, so how does that happen? The idea is that as you make movements, your brain can predict the consequences of it. Let me show you that in this experiment. So here's your hand position in black. Eye position is in green. And so all the person is asked to do is to look where they think their hand is located. So they can't see their hand. The hand is below the screen here. But they're moving their own hand. And if you look to see where they're moving their eyes, they're moving ahead of the hand. They wait for the hand to catch up. They move ahead of the hand, and then so forth. So basically, the eyes are looking about 200 milliseconds in front of the hand. So as the person is moving their hand, they are looking about 200 milliseconds in front of it. They are predicting where the hand is going to go as they make that movement. On the other hand, if you passively move the hand, so if the machine holds the person's hand and moves it around, and if you look at where their eyes are in this green here, it's lagging behind the position of the hand. So if all you have is sensory feedback, your eyes will tell you that my hand is someplace behind where it actually is. So through prediction, you can have a sense of what the future is. Now let me show you something about the brain and how it does that. So whereas the basal ganglia has a lot to do with that value function and describing cost and effort, the cerebellum has a lot to do in predicting the future. This task, for example. So let me show you an example of this patient is missing her cerebellum. So she was born with this incredibly rare disease that makes it so that she goes through a life without having a cerebellum at all. And it's interesting to look at how she behaves in a task that requires prediction. So what she's doing is that she's going to hold a force transducer in her right hand, hold the ball in her left hand, and then drop the ball onto a basket. So if it is you doing this task, then what you should do is that as you drop the ball, you should anticipate it's going to hit the basket. And therefore, right at the right time, grip it a little harder when the ball is expected to hit the basket. Does that make sense? So you're predicting when that's going to happen, right? On the other hand, what if it's me that's holding the ball and I'm going to release it? Well, in that case, you don't know when I'm going to release the ball, and therefore the best you can do is react to when the ball hits the basket and only then grip the transducer. Does that make sense? Yeah, you see that? If I do it, you can't predict it. If you do it, you can because it's you doing it. So the point is to show you that the patient cannot predict the timing of this ball hitting the basket, whereas the healthy individual can. All right. So in the first part of our experiment is what we have is that we just look at the sensory feedback. So in this case, the experimenter, me, I'm releasing the ball. So neither the healthy individual nor the patient can predict it. And so what happens is that when the ball impacts the basket right here, sometime later, the hand grips the force transducer. And you see the patient does it as well. Noisier, but they can do it as well. What this says is that the patient has sensory feedback. They can respond to that stimulus. But now let's look at what happens when the experimenter doesn't drop the ball, but the patient drops the ball. And we'll compare that to the healthy individual. So healthy individuals on the left side. So the ball is going to impact at this point. As you notice, before the ball has impacted, they already are they're pushing the force transducer. So in anticipation of the ball hitting, they have begun to hold the transducer higher. On the other hand, in this case, you notice that the patient is missing that entirely. So there is no anticipatory change in the grip force in anticipation of that action. Okay, so I'm going to skip this. I'm going to show you one last thing to talk about the basal ganglia. We talked a little bit about patients and the cerebellar damage. Let's talk about basal ganglia and its effect on movements. So we talked about this notion of having a cost, that we have this effort that we're going to have to spend and we're going to get some reward for it. So in Parkinson's disease, there's a degeneration of these dopaminergic neurons. This results in severe loss of dopamine in the basal ganglia, especially in an area called the putamen. These patients exhibit slow movements, very low voice, very small handwriting. And I want to give you an example of that. So this is not a PD patient, but this is a stroke patient with damage to their basal ganglia. In this case, the left caudate nucleus of the basal ganglia. So the patient is asked to copy these letters, T, B, Z, E. When the patient does it with the right hand, they write in this tiny script, whereas their normal hand, the left hand, they write bigger. So what this can be telling us is that this desire to write, which requires effort, and of course the larger the letter, the greater the effort, is somehow resulting in this imbalance between the amount of effort that's associated with the task and the amount of reward. So we think of micrographia, like you see here, as tiny movements that are taking place because there's this differential representation of reward and effort. For some reason, on the arm that's affected, this is viewed to be the same amount of effort as this, despite the fact that this is much bigger letters than what you see there. Okay, so let me summarize. We have a nervous system in order to make voluntary movements and acquire reward. There's a question of what to do, which is associating reward to a location on a spatial map or associating reward to arbitrary visual stimuli. Spatial maps require the hippocampus. Arbitrary stimuli require the basal ganglia. One of the brain's reward signals is the neurotransmitter dopamine. Dopamine encode reward predictions. Then there's a question of, okay, there's a reward there, but how do I get there? And so we have this expectation of reward, and we have some effort costs. And this forms policies. These policies determine how we should produce motor commands. In our brain, as motor commands are generated, we make predictions about what should happen, the sensory feedback. We think the cerebellum is crucial for predicting sensory consequences, these models that say, if you produce this action, here's the effect that's going to result, whereas the basal ganglia receives reward signals. So it's likely important for forming policies that says what we should do, how we should do it, how much effort to expend, what reward to expect. Any questions? Okay, I'll see you Wednesday.